Okay, any questions or specific problems we need to deal with? That's the right, yeah, that's the right one. I've highlighted 24 out of whatever the total is in version 2. And if we're missing any that you had problems with, then we'll hit those too. You can think of them now, or if they pop into your head when we're going through, just stop me and we'll deal with your issues first. Otherwise, I'll just take the highlighted ones, and that means I got about 5 minutes each on average, which is going to be a tall order for me. Let's look at number 1. So we've got, I'm not going to write that equation on the board because the question is really, really simple. If the reaction is first order well, let's read it backwards actually. What would be the preferred format for the rate law? Remember, we just write rate here. Nobody's asked me this. We just write rate here because the units of the rate might vary depending on your experiment. And so we just say whatever the rate is as a constant. And then the first factor is going to be, and we're dealing with reactants only. So the first one is hydrogen peroxide. And the conditions say it's first order, right? Okay, so just like that. The iodine is second order. Like that. And the hydrogen ions are 0. So what's the preferred format? Well, keep this one, keep this one. That one, anything to the 0 order is 1. So we don't need it there. That's redundant. This is the preferred format for those conditions. So if any student's going to get it wrong, they usually go for A instead of leaving that hydrogen ion out. But the correct answer is E. Right, number 2. Reaction has this rate law. K equals A squared, B to the first power, C squared. What's the overall order of this reaction? Remember how to do that? Simple math. Just add them up. 2 plus 1 plus 2 is 5. Okay. So this is total order, or overall order, equals 5. Let's see. I'm going to skip this one because we've got, this is be an initial rates problem. Actually, this is not initial rates. This is a mechanism problem. And I think I got to looking at it, and I think it's a little steep for this class. So we're going to skip over that one. I mean, if you can do it, that's great. But I'm not going to hold you to that one. Let's look at number 4 instead. Because working with mechanisms in kinetics takes a lot of practice and many hours and time to get really good at it. I don't expect it to be, no. If something like that would be on the exam, it'd be a bonus anyway. Yeah. And I might add, we're going over these because I think these give you the highlights, the most important topics that we covered. But that doesn't mean you're going to see this exact question on the exam. You know, I've been known to be sneaky and change conditions. So if you memorize the answers, chances are it's probably 50-50 or you get it wrong. So number 4, if the reaction 2, hydrogen iodide, yields what? Diatomic hydrogen and iodine. Okay, is second order. So what do we mean by second order? Typically, if it just says second order for this type of reaction, it has to be hydrogen iodide, because we're working from initial rates. So it's always the reactants that we're interested in. So if we wrote the equation for that one, it would simply be HI2. And the fact that this is 2 and that's 2 is coincidental. Right? There's no direct relationship there. The only way we could prove that as a coefficient is if we had a mechanism to work from. Then the mechanisms allow you, for the elementary steps, to use coefficients. But the overall reaction, you can't use coefficients. This has to be experimentally determined. Okay, what's the question? Which of the following will yield a linear plot? Okay, if it's second order, what gives you a linear plot? Remember those three? We have the 0 order, we have the first order, and we have the second order. And they're all x-axis is time. So this is actually going to be the concentration. This is going to be the natural log of the concentration. And this is going to be inverse of the concentration. Okay? This is 0 order. This is first order. This is second order. So the plot of inverse of concentration versus time is going to give you a straight line. It should go like this. So if we plotted these same values, if we plotted the raw data here, we plotted the natural log here, you get curves like that. This proves that it's second order. So B would be the answer. The inverse of HI versus time. Okay. Question? Oh, okay. Light bulb go on? Okay. That's 4. Okay, number 5. Let's see. Okay, that data goes to 6, so 5 is by itself. Which of the following statements about enzymes is incorrect? So we got A through E. And E is all are correct. All right, so we got to find, if we find one that's incorrect, we can stop. All right, there are usually proteins that catalyze specific biological reactions. Is that a reasonable statement? Yeah, they're usually proteins. Not all of them. Some enzymes are RNA, but most of them, the vast majority, are proteins. And they catalyze specific biological reactions. And in fact, they don't just catalyze specific reactions, they only go in one direction for most of them. There are a handful that are troublesome. They work both directions. And that's been the bane of agronomist existence for quite some time. So B says they are equal to inorganic catalysts in efficiency. I don't know if I mentioned that in our discussion. Did I talk about efficiency? Maybe it was a veiled transmission. The efficiency of inorganic catalysts is very low. It's like 1%, between 1 and 10% conversion. Increase, let's say, if you're looking at rates, the efficiency is going to be maybe 1% greater or 10% greater with an inorganic catalyst. The organic catalysts, the enzymes, they are massively more efficient. You're talking about 50% or better speed increase. So this one is the false one. We found our answer. B is the incorrect one. If we look at the other several thousand are now known, yes, probably over 10,000. Molecules they react with are called substrates. I didn't mention that before. When an enzyme reacts with something, it's called a substrate. If you go on, well, no, nobody's going to do organic or biochemistry in here. You are going to do it? Okay. You're going to, yeah, substrate's going to come back later. Okay, so that's true and that's true, and B is our false one. Let's see. We're going to skip this one too. The following initial rate data were found, and this asked you for the entire law. If I were to put this type of question on the exam, it would take you half the time of the exam to finish it. That's why I'm probably not going to give you one this complete. I mean, if you can work that, then you can do any other question that I'm going to give you. But as far as putting that whole thing up there, I'm not going to do that because it just takes too much time. You need to understand why it works and the procedure. We're going to skip that one too and go to number 8. A free radical is a chemical species that possesses what? We talked about that, right? A free radical? A free radical has an unpaired, at least one unpaired electron. But what would be examples of a free radical? A hydrogen atom. Not the hydrogen at room temperature and pressure, H2. A hydrogen atom is a free radical. Any of the diatomics would be good candidates. Or let's see, oxygen. If you had an oxygen, it would have 2 unpaired electrons. Okay, and that's not only bared out with the Lewis dot structure, but with molecular orbital theory will give you 2 unpaired electrons also. Any of the halogens, if they're single atoms, they're free radicals. Now, this is elemental free radicals. You can also have free radicals that are molecular, like large molecules that have 1 or more unpaired electrons. And those are the nasty molecules that natural cell processes produce as a byproduct. And they're very reactive and they're destructive. They damage cells. So when you see advertised in the popular media, free radical scavengers, or you eat something that has very high in unsaturated fats, those are free radical scavengers, and they help protect your cells. Vitamin C is well known as a free radical scavenger. That's probably why Linus Pauling used to eat mega doses of that stuff every day. Okay, so D, an unpaired electron. It could be 1 or more unpaired electrons, but D is the best answer out of that bunch. Now, there is an example there of a free radical, but by definition, the best answer would be D, unpaired electron. Oxygen atom is a free radical, but it's not the best answer because it says a free radical is. No, a free radical is an oxygen atom. It's just we're looking for the best answer. Now, free radicals can have charges or they can be neutral, either way. I think we ran into one before drawing Lewis dot structures last semester. Was it nitrogen dioxide? It had, when we did the Lewis dot structure, we had 1 electron left over. Where do you put it? No. Well, that makes it a free radical. Unconventional political views, of course. I just couldn't think of anything else to put in there, so threw that one in. So the best answer is the one I'm looking for. That's the one that covers all possibilities, and that's the unpaired electron. Number 9. The rate expression for a particular reaction is rate, excuse me. Dyslexia is kicking in here. Excuse me. A and B. A's first order and B is second order. If the initial concentration of B is increased from 0.1 to 0.4, so if we start off at 0.1 molar and then we progress and we try it again at 0.4 molar, the rate will increase by what factor? Notice that we're looking at a change in B in terms of multipliers. It's not just going from 0.1 to 0.4 is 0.3 change. We're talking about multiply. How many times bigger is it? Because we want to know how many times faster is that. So the change here is times 4. Okay? So 4 squared is 16. This is going to be times 16. Be 16 times faster. Okay? Divide this one by that one.
Yeah, but for the square it because of the exponent on the.
Yes, yes, it goes right in there and we square that value. Let's see, number 10. We'll just leave that there for now. Number 10, for which order reaction is the half-life of the reaction proportional to 1 over K? So we got 0 order, first order, second order, and we want to do the half-lives. So what's the half-life for the first one? Well, we can go to useful information. I think I put it down here. This would be a good time to check, be sure. Let's see, let me get these things out of the way. Here we go. So you just have to know what you're looking for. All right, so over on in this right-hand group over here, the first one is 0 order, and its half-life is A0 divided by 2K. A0 divided by 2K. I remember this one, 0.693 divided by K. And the last one is 1 over, which makes sense because the 0 order is reference to inverse of the concentration. So this is K times A0, right? Yeah. Okay, so if we go back to number 10, close. There we go. Go back to 10. The question is, which of these is proportional to 1 over K? Any ideas? All of them. Right? All of them. K is in the denominator for each one of these. So this is proportional to 1 over K. It's like writing this over 2 times 1 over K. Okay. So they're all proportional to the inverse of K. Fun facts. That's why D is the answer. Let's see, number 13. Sometimes when you're studying a new subject like this, it happens in not just in chemistry, but any subject, especially the sciences. You get down in the weeds so deep, you can't see where you are. And if you back up and look at them from an elevation, you can see trends. So Number 13. Okay, of the following choices, which type of collision is most likely to be the rate determining step in a proposed mechanism? Now, that question assumes that you take it to mean um, all of these types of mechanism, the elementary steps, are part of the mechanism. So one of them will be the slowest. The one that's least probable to occur is going to be the slowest. Right? Unimolecular, right? It's only got one molecule, and all it has to do is just split or change something, right? It's going to be the most likely, the quickest. Bimolecular, you have to bring two together with the right energy and the right orientation, right? So it's a little less probable. Termolecular is almost infinitely impossible. I mean, they do happen, but they're very rare. There's no such thing as non-molecular. Well, unless we're talking about atomic, but we haven't studied that term. So termolecular, C, is going to be the slowest step, just out of course. Now, that's the most probable choice. I've seen examples where you have several steps, elementary steps in a mechanism, and through experimentation, it's determined that one that maybe a bimolecular is slower than a termolecular. It's strange, but it does happen. But on the basis of probability, we would expect the termolecular to be the slowest one in there. That's the best answer for this question. All right, 14. Let's see. The reaction of hydrogen peroxide yields water and oxygen has the following mechanism. Okay. So we're giving it a two-step mechanism here. That doesn't mean that this is definitive. It's just proposed for this problem. This two-step mechanism, we get hydrogen peroxide combining with an iodine ion. And then it produces water and the IO minus ion. And then that reacts with hydrogen peroxide and produces water, oxygen, and reconstitutes the iodine ion. Okay, so the question is, what's the catalyst here? Number 14. If we have this step yields water plus IO minus. You know what? I'm going to take this opportunity as a teaching moment. This is step one. Then step two takes another hydrogen peroxide plus this one yields water and reconstitutes the iodine. Oh, I left out oxygen. Sorry. I would eventually figure that out. Because if you add these two together, it has to be that equation. Okay. So, which is the catalyst? It's the one that goes in the front and comes out the end, apparently unchanged. This is the catalyst right here. It goes in this end, comes out that end. It participates in the reaction, definitely, but it appears as if it's unchanged. And it doesn't appear in the overall mechanism. If we put it there, we would say something like this. That's where you put your catalyst. And in fact, the solution that's introduced here is usually in that arrangement. You have some molecular iodine and some iodide ion. Anyway, now also I want to make another point, which is not one of these questions, but which one is the intermediate? is the one that's produced in the reaction, but disappears before the reaction is complete. So this is the catalyst. And this would be a homogeneous catalyst. This all occurs in solution. And this is the intermediate. We know this one because we put it in there. We don't know this one, usually, because we can't detect it. Okay. All righty. Let's see who's next. Let's skip a few. Get down to this one. Okay, we are going to use some initial rates information, but we're not going to try to calculate the entire all the orders for the rate plus the K value. We're just going to do one. So this shouldn't take too long. All right. So there's our equation. We have the manganate ion. We've got oxalic acid. We've got hydrogen. Did we do this in class? We did this one in class, didn't we? Yeah. Well, okay. Well, it bears repeating. What's the order of the rate law with respect to MnO4 minus? We do need to know the rate law expression in generic terms. So we're going to have the manganate ion to its order, and then the oxalate ion, H2C2O4, to its order, and then the hydrogen ions to its order. Now, so that's what we're basing our whole procedure on. If we're after the order for the manganate, we want the two experiments where these two factors are constant. They don't change, but this one does change. Okay. So which ones will those be? Be the second one and the first one, right? Yeah. So if we put we're going to write this out for the second one first. And remember the reason I do that, because the rate is bigger for the second one. And if it's in the numerator, we get a whole number, not a fraction. Okay, so the rate for the first one, second one, excuse me, the second reaction is going to be the rate for the second is 8 times 10 to the minus 4, whatever the units are there, molarity per second. And then we have a K for that one. And K is the same one for both of them, actually, because K is a constant. And then we have a value for MnO4 minus, which is 2 times 10 to the minus 3 molar, right? And its order. And then we have oxalate, which is 1 times 10 to the minus 3 to its order. And then the hydrogen ions, 1 to its order. And then we divide this one by the first equation. And its rate is 2 times 10 to the 4th, minus 4, excuse me. Same K, different value. That's the way we designed it. And then these are the same. Okay. So when we reduce this whole equation, this quotient, we find that this term cancels that term. This term cancels that term. The constant cancels. And now this is 2 into 8 is 4. And this one is 1 into 2 is 2 to the n power. So n has to be equal to 2. Okay. Not just any. You have to be selective, right? You want, if you're trying to get at this value here, you want these to change, but you want those to be constant, unchanged. Yeah. And when you set up the series of experiments in the beginning, you choose those values so that you get access to each one of these changing. That's why you need, if you got 3 reactants, you need 4 equations. That way you have 3 comparisons. Because this term changed from 1 to 2, and the other 2 didn't change.
Oh.
The rate, okay. And the reason I put 2 on top is simply so I get a whole number. Yeah. I mean, technically you could do it with 1 on top, but it might take some mental gyrations to get there. 17, 18. 18, does it refer to this one? No. 18 is by itself. Diagram is for a different question. Okay. Rate law for the reaction, 2NO plus O2 yields 2NO2 is this. So they're giving us the rate equation. Is second order and O2 first order. Now, those are the only 2 reactants. We don't have any zeros orders in there. Right? NO is second order, O2 is first order. What happens to the rate when the concentration of O2 is tripled? All right, so we're getting back to a similar situation to that previous question, but I'm going to expand it a little bit. If we triple this one, if we say 3 times that one, is to the first power. So this one's going to be 3 times. Okay. If we did 3 times here and only 1 time there, like this stayed constant, and we did 3 times here, then that would be 9 times there. Okay. What if we said, I don't know, 4 times here, and we had 2 times here? So that would be 4 squared to be 8, right? No, 16, excuse me. 4 times 4 is 16, times 2, it would be 32. 32 times the increased rate. Okay? Let's see. We're going to skip this one. We've got another reaction diagram down the road, so we don't have to do that one. Let's see. That looks like a duplicate. Catalyst. Yeah, it is. 21's a duplicate. Y'all notice that? We already covered that one. I don't know how that slipped in there. Let's see. Okay, how about this one? 24. What fraction of a reactant remains after 5 half-lives of the first order reaction? Well, actually, let's see. You guys that had me last semester, you've heard this before. What's the main purpose of a word problem? Okay, yeah, that's the whole point of a word problem, to confuse you, to see if you really know what's going on, and to pick out of the word problem the information that you need, throw away the rest. This is one example. It doesn't matter. 5 half-lives for a first order reaction is the same as for any order reaction. It's 5 half-lives. Half now, another half-life, half cut again, half again. Whether it's 0 first or second order, it doesn't matter. So if we go through 5 half-lives and we start off with 1, then we go, let's see, half-lives. Or if we start off with 1, then after the first half-life, we get a half, right? So that's 1. The second half-life, we get a quarter. The third half-life, we get an 8. Fourth half-life, we get a 16. And the fifth half-life, we get a 32nd. Okay, so 1/32 is the answer. After, yes, 1 over 2 to the fifth, right? That's the easy way. Yeah, from 1 over 2 to the fifth is, oops, 32. Yep. Did any of you like all your math classes when you were going through? Yeah, I could tell. Okay. Let's see. 25. 25, we'll use that table just above it. So the following question refers to this reaction: 2A2B2, 2A2B2 yields 2C. Something burning? Smells like a fireplace, doesn't it? Something's on fire. Oh, I know what it is. Yeah, right across the road. That's where the new extension is coming through, bypassing Beaver. Yeah. Yeah, they're going to build a road. Uh-huh.
There was a truck right out in front of me today. I was like, yeah.
Yeah, it's supposed to relieve the traffic pressure in Beaver. Uh, so it's if you drive down toward Beaver, you'll see that I think they're going to cross just this side of the lumber yard. It used to be a small apartment complex right there. It's gone now. Okay, so we're proposing this mechanism. Step one is fast, and step two is very slow. Okay, and I'll just put this up here because I haven't read the question yet. That's B2 yield R plus C. And then we have that one plus R yield C. So first thing you'll notice is if you add these together, you get two A's, get one B, you get two C's, one here, one here, one here, and this intermediate goes out. So this mechanism, at least up to this point, is kosher. But what's the question? Which step is rate determining? Oh, the rate determining step is the slowest one. Right? That's the rate determining step. And if we were to try to derive this one from this information, we would start with that one. Like we would say something like this: rate equals some K. That's the K for this reaction. And then we'd say that's K, and then we'd have A2 to the first power. Oh, and R, excuse me. And R to the first one. But we'd have to get rid of R. So we'd have to produce and if this is a fast, it doesn't say it's a fast equilibrium, right? That would be helpful if it was equilibrium. Then we'd have a reverse. It'd be easier to get rid of the R term, but that's where you would start anyway. Those are the types of problems that advisors give their graduate students to tackle, because it takes a lot of time, and most advisors are professors with very little time. They're busy raising money. Which step? Oh, we did that already. 26. Here we go. For a reaction where we have yield products, A0 is 6.4 molar, and the first two half-lives are 60 and 30 minutes. If this reaction is known to be zero order, calculate K. Okay. So I would set up a table. Right? We have the concentration of A, and we have time there. Then at time 0, we have 6.4 molar, don't we? 6.4 molar. That's where we start. The first half-life is 60 minutes. So we know this jump from here to here is going to be 60 minutes, and it's going to give us 3.2 molar, half the concentration in that amount of time. The second half-life is 30 minutes. So we're going to go here. This gap here is 30 minutes. So now we're down to 90 minutes for the next half-life, which would be, let's see, 1.6, right? Did I do that right? 3.2 divided by 2. What's 2 times this? Yeah, that's right. Okay, so that's given. And the reaction is zero order. So the rate equals K times A pump. Zero order, that's it. The rate is equal to K. And he wants us to calculate K. All right, so a zero order reaction, half-life, is equal to, let's see, this is, somebody look it up, tell me. I don't have it. What's the half-life for zero order? Is it 2K down here? Yes. Is that right? Check it out, be sure.
Yeah,
Over 2K. Okay. So all we need is a value for this and a value for that. We can solve for K. So I would take the first one. Just say 60 minutes is 6.4 divided by 2K. And then we solve for K. So K is over here. We put 60 over there. That's 6.4 divided by 120. Right? Did I skip too many steps? I brought K over here, put the 60 over there times 2 is 120. So it's 6.4 divided by 120, which is 5.3 times 10 to the minus 2. And it said we didn't have to put units in it, right? Yeah, without units. So that's C. Best answer. 5.3 times 10 to the minus 2 is K. We should be able to do the same thing with this one. Say start with 3.2 and put 30 in there. So 3.2 divided by 60 is the same as 6.4 divided by 120. So yeah, we should get the same answer. Okay. All right. Number 27. This question, according to collision theory, the activated complex that forms in step 1 could have which of the following structures? So the activated complex, remember, is when you are, let's see, I'm going to use an exothermic reaction. And this is the progress of the reaction. So I'm going to start here. It's going to go up like that, like that. So the activated complex is right here. So what's actually happening at the activated complex? This is theory. What do we think is happening? At this point, we are starting to break some bonds and form some new ones. So in our representations here, the dotted lines are partial bonds. They could be bonds that are in the process of breaking or in the process of forming. So if we've got, let's say our equation is, no, it's not using that one. Not using anything. Could have which of the following structures? I thought there would be an equation to go with this. Oh, it does. Where we have, let's put that up here so I won't get lost again. R plus C. This is very slow, and this is just slow, which is A squared plus R C. So the very slow is the rate determining step. That means we're going to focus on this one. So A squared, A sub 2 and, well, A2 and B2 come together. And what are they going to do? Well, the A2 would be like this to begin with, and the B2 would be like this to begin with. And when they come together, if they're going to produce something else, then on their way up to this point, you still got A's and B's. But now, these bonds are breaking, and well, let's see, they put them the other way. Let me be consistent with the way they're writing it. A here and B here. So these bonds are breaking and these bonds are starting to form. But this is the only thing that we can draw from that, because this is the rate determining step. This has to be the case. Now, what may come out of this, once the bonds are reformed, we may call AB something else. We may call it R, we may call it C. But according to the collision theory, when it gets to this point, then we've got partially broken and partially formed bonds. So, and if you look at the others, you know that A can't be it. It's funny the way the Microsoft Word works, but A is referenced to that block above it to the right. Okay, A doesn't reference the one below it where AA and BB are together. That's B. See what I mean? Right. If A goes to these guys up here, and B goes to these. So in the activated complex, we can't have the new molecules yet, right? We can't have the R and the C. We can only have what we started with. So if we've got anything in there besides A's and B's, then it won't fit. It does no work. So A can't be it. B is a good candidate. C can't be it because it's got R's. And D can't be it because it has R's. And is there an E? Yeah, E. E has A's and C's are not there either as reactants. So actually, process of elimination gives you B as the only possible answer for that activated complex, according to the collision theory. I threw that one in there because some of these diagrammatic type problems and solutions are difficult to follow. It's like last semester. No, it's this semester. Wasn't it? Or was it last semester? We had the little boxes with different circles and squares and triangles and stuff put together. Don't remember. Okay, let's move on. How about, there's another monster right there. Okay, how about this one? B, 31. We're expecting the answer to be B. The rate constants for a reaction at two different temperatures are given below. So with these two different temperatures and different rate constants, What are we getting at? The activation energy. What is the activation energy for this reaction? And all we have to do to find that one is to go to our useful information and look for the integrated Arrhenius equation. Natural log of K2 over K1. And that's what this could be any two. Lowest temperature, higher temperature, I would say. And then the rest of the equation is E sub A over R. And this is the inverse of T1. Is it minus or plus? Minus 1 over T2. There we go. And the temperatures have to be in Kelvin. Right? So 30 plus 273 is 303. That's T1. And T2 is 49 plus 273. 322. So this is T2. So what's the K for the first? The low temperature is 1.38 times 10 to the minus 4. And T2 is 1.21 times 10 to the minus 3. 3. This is our unknown. This is a constant, 8.3145 joules per mole K. And then 1 over T1 is 303 minus 1 over 322. And we solve for E sub A. And let's see if this works. Okay. That one and divide by 1.21 exponent minus 3. Divide that. So I get 1.14 for this. 1.14 times 10 to the minus 1. Then take the natural log of it. That's minus 2.1714. Then we have E sub A divided by the R. And then I'll do these separately. So 303, take the inverse somewhere. Here it is. And then 322 and take the inverse. Subtract that. This gives me 1.97, 10 to the minus. Okay. So this is in the numerator, that's in the denominator. I'm going to divide this one into that. And that gives me E sub A times 2.342 times 10 to the minus 5. And then if I divide, I'm going to get a negative number. I wonder if this formula is written correctly. I put them in the wrong place. Right? Is this K2? No, that's K1. See? That should be down here, and this should be up here. Because that's K2. All right, so what's the fix for that? Take the inverse of that number. Right? So 1.14 inverse. So this is, swap these. And this is 8.7719, and take the natural log of that. 2.1716. Now we're talking. Okay, this is correct here. So I just need to divide that into this, correct? So E sub A then I'll just divide this by that number. Let's see, 2. And this is 9.28 times 10 to the 4th joules, because this is joules per mole K. But our answer is not in joules, it's in kilojoules. So what would that be in kilojoules? $92.8 kilojoules. Rounding error, 92.7. Okay? It's the small things that trip you up. Good on time. Okay, it's only 10 o'clock. That's good. How about 32? In the following balanced equation, the reaction and experimental results follow. So we've got concentrations and rates. What are the rate law orders for NO and H2? Okay, so this one should be fairly simple. Right? It's not quite as complex as the other. We've got values for NO and H2 concentrations, initial concentrations, and then the rates that are assigned to each one. We have 2 reactants, so we need 3 equations. Okay. So if we're looking at the rate law here, it's going to take this form. The NO, NO, to its order, and then H2 to its order. Okay. So this is the equation that we're going to use to ratio. If we're getting that NO, we want the one where NO changes, but H2 doesn't change. So I would say first one and third one. Right? First one and third one, NO changes, but H2 doesn't. So, and I'm going to put the third one first. So the third is here, and the first is here. And then we're going to ratio them. So what's the rate for the third one? 2.40. And the first one is 0.60. Okay. Then we have this value for NO. For the third one, it is 0.30. 0 threes. Yeah, there we go. And then we can save ourselves some time just saying that's going to cancel anyway. And K is going to cancel also. So the first one is 0.15. The N, and then that one cancels for the hydrogen. This one cancels for the K, and we get 0.6 into 2.4. What's that? 4? 4 times 0.6 is 2.4. And that's equal to, oops, got a 0. 0.015 into 0.030 is 2, isn't it? To the N power. So N equals 2. So now we have this one is 2. Okay. We got the order for that one, it's 2. So it's either C or D. Now we want to compare the ones where hydrogen changes and NO doesn't. So that would be 1 and 2. So this would be the second one. Okay. And this is going to be 0.015. This is going to have actual values for the hydrogen. So for the second one, that's 0.040. And for the first one, is 0.020. Okay. The rates change also. For the second one, it's 120. And the first one is still 0.6. So far, so good. Okay, divide these in here, that's a 2 in there. Divide that one is a 2 to the n. So n equals 1. This is 1. Okay, so the answer to the question is C, 2 and 1. What if we wanted to find K? How would we do that? See, I got sneaky and said, instead of the orders, it just gave you the orders and says, what's K? You would take this equation, you would take any one of those experiments, just take the first one, 0.60 equals K, and the concentration of N for the first experiment is 0.015 squared, and hydrogen is 0.020, the first power. Okay, then we solve for K. So I'm going to do these all in one step. Square that, multiply it by this, and divide by that. Excuse me, divide into that. This is 0. Maybe I better do this. There we go. I just took these two terms and put them over here, and then I swapped places, put K over here and put that over here. That's all I did. So 0.6 and then 0.015, I'm going to square that, divide it into it, and then 0.020, divide into that. So K is 1.33 times 10 to the 5th. Okay. This is probably going to be a pretty fast reaction because that's 10 to the 5th. Put that here and put any concentration in here. The rate's going to be up there. This is a very fast reaction. Yes. Or if this appeared on a test, I would probably give you the orders and ask you for K. Otherwise, it'd take you half the test to do it. Half the allotted time, I should say. Okay. 33. First order decomposition of H2O2 at minus 28 degrees occurs with a half-life of 50 seconds. Starting with a concentration of 25.2, what will be the residual concentration? That's bad sentence structure. There should be a comma after the H2O2. And what shouldn't be capitalized. Starting with the concentration, 25.2 of hydrogen peroxide, what will be the residual concentration of H2O2 after 5 minutes? Okay, let's put this into a first order decomposition. So we're saying that, and we actually don't have to know what the products are. Because we've been given its first order. So the rate equals K H2O2. But we're talking half-lives here. So we also need to know the first order value for half-life. And we did that one before, didn't we? A0 over 2K. Starting with a concentration of 25.2, what will be the residual concentration after 5 minutes? Okay, a half-life is 50 seconds. This is 50 seconds. Okay. So if we want to find out what, we're going to need the first order, let's see, the first order integrated rate law. Right? That uses the natural log. H2O2 equals minus K T plus natural log of H at any time 0. If we take the actual time 0, then the T in solving this equation is going to be let me be accurate. The T in this case is going to be 5 minutes, right? So 5 minutes, if we calculate K from this, it's going to be in reference to seconds. So this value needs to be in seconds. 300 seconds. Okay, that's our time interval. But we need to find out what K is. So what's the initial concentration? Let's see. 50 seconds is the half-life. And if our initial concentration is 25.2, right? Divided by 2, and then we're going to bring the 50 over here and put the K over there. Right? I just move K over here, put 50 over here, and that's the expression we get. You're right. Thank you. Over. Okay, correct? Okay. Now, let's see. This needs to be redone. Put the K on that side, and then move the 50 underneath. There we go. So let's see what K is. This is 1.386 times 10 to the minus 2. Okay, so now we can take this expression, the natural log, and this is our unknown. This is what we want to know right here. The actual concentration after 300 seconds, which is 5 minutes. And the initial concentration, we're going to use that same value as before. We didn't. No, we didn't use the concentration yet. It's 25.2. There we go. Wait a minute. Oh. Starting over. Okay, the half-life. Yeah, that's right. Right, 50 seconds, half-life. Yeah. So that's the K. All right. Brain farts. Okay, so let's resolve this side first. Natural log of 25.2. Okay, that's 3.2268. And then this term is 300, 1.386. Exponent is 2. Updates. Yes, change the sign. There we go. This is minus 4.158 there, plus 3.2268. And that would be minus 0.9312. So how do we get this value? From that, we just take the anti-log, which is e to that power. And let's see, punch that key, and that gives me what's left over. 0.39. molar. Okay. Too much math. Yeah. All right. Let's see. 33, 34 coming up. Hour. For the second order reaction, NO plus O3, ozone, yields NO2 plus O2. The rate constant has been measured to be 1.8 times 10 to the 7th at 298, and the activation energy has been measured to be 11.4 over the temperature range 195 to 304. Okay, that's good. What's the rate constant at 233 K? All right. We need the integrated Arrhenius equation again. Okay. So let me put that over here. K2 over K1, I think. Yeah. And then E sub A over R. This is 1 over T. 1 minus 1 over T, 2, I believe. Yeah. Okay. So let's extract information from that thing. The activation energy has been measured as 11.4. So E sub A equals 11.4 kilojoules per mole. Okay. The temperature, the first temperature, the low temperature, which is usually the way we interpret this, the rate constant at 298 K. So at T1 equals 298 K, the K1 equals 1.08 times 10 to the 7th. And we want at a temperature of 233 K. Okay, that's a lower temperature, isn't it? So why don't we make this one 2 and this one 1? I think it'll work out better if T1 is the low temperature and T2 is the high temperature. So this is 2. This is our unknown. Now, do we have enough information? We got values for these two. That's a constant. We got this one, and we got this one. We can solve for that one right there. Except R tells you the units that you need. 8.3145 joules per K mole. This needs to be in joules. So remember how we convert kilojoules to joules? We take the equivalent of that, which is 10 to the third. 11.4 times 10 to the third joules. Okay. That's not scientific notation, but it'll work. You can punch that into your calculator. It doesn't care. Okay, so now let's fix it. We've got K2 is 1.08 times 10 to the 7th, and then K1 is our unknown. Then we have E sub A, which now is 11.4 times 10 to the third over R, which is 8.3145. We usually put units up there, but if we're careful and we've taken pains to match units properly, then we should be okay without them. The first temperature is 233. Second one is 298. So these are all numbers we can resolve this side with a calculation. Let's see. 233, I'm going to take the inverse, and then 298, take the inverse and subtract. So that's 9.36 times 10 to the minus 4. Then I'm going to multiply that times this value, 11.4 exponent 3, and divide by this value, 8.3145. And I get 1.284. Now, here's the trick on this side. How do we get that out of this natural log? You need to know rules for logarithms. The log, it can be natural log or common log. The log of A divided by B is equal to the log of A minus the log of B. That's a logarithm rule. Okay. We had to, when I went through math class, we had to prove it. I hated proofs, but there it is. So we take this one and we say the natural log of 1.08 times 10 to the 7th minus the natural log of K1. Go. Now we can get at that K1. So we need this one, and well, let's get that value first. And then I'll show you what to do with it. 1.08 exponent 7 natural log. Here. This is 16.195 minus log of K1 equals 1.284. Okay, the way I would do it, I want to get rid of that negative sign. So I'm going to move this over here and move that over there, which makes it negative. So 16.195 minus 1.284 equals log K1. Okay. So I'm going to take that this value and subtract 1.284. And that's 14.4. Oops. 14.911 equals K1. K1, then it's equal to E to the power 14.911. Let's see. There it is. This is 2.99 times 10 to the 6th. Close enough. C. That's your best answer. I used a lot of extra decimals in here. That's probably why my number didn't exactly agree with that number. And hopefully, if I give you one like this, I won't put none of the above. Because if you come out with that number and you see that number, you say none of the above, obviously. And if I mark it wrong, then you can bring it to me and prove it and get credit for that question. That's the way it works. Okay, 34. And skip a few. Here, we want this one. This is 39, 40, and 41, I think. Yeah, for this graph. Okay. Yeah, 39, 40, 41. So 39, 40, 41. All these reference that graph. Okay. I'm going to put the questions up here. Which letter shows the activation energy without the catalyst? So this is E sub A without catalyst. And 40 wants with a catalyst. E sub A with catalyst. Okay, and then 41 is activation energy for the reverse reaction without the catalyst. E sub A reverse without catalyst. Okay, so that's what we're looking for. All right. And it looks like A, B, 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 C. Okay, so the selections correspond exactly with the letters in the graph. So here's the graph. And we're looking for the first one, E sub A for without catalyst for the forward reaction. So we know it's the peak on that red curve related to the reactants line. And that looks like E gives you that one, doesn't it? It's equal to E. With the catalyst would be A, right? The blue line. Going from reactants to the top of the blue line be A. And then the reverse reaction would be from the products to the top of the red line, which would be C. Okay? So we should have EAC for those answers. EAC. There we go. Yep. Questions about that one? Strangely enough, some of my students always get confused with this. It seems very straightforward to me, but I've been at it for a while. Okay, got another graph. Okay, what are we going to say for this graph? 42. What's the value of rate constant? Okay, so we got 42 and 43 are referencing the graph. Okay. Excuse me. So let me put the problems up here and the questions related to them. Then we can go back to the graph. So 42 wants the order of the reaction with respect to SO2, CO2. So we want the order. Order for SO2, CO2, is it? Yeah. So that would be some value. Okay. And 43, what's the value of the rate constant? So what's K? All right, let's go back to the graph. We got a straight line with a negative slope, time against natural log. What order is that? First order. 0 is the raw data, natural log is first order. So M equals 1. How about K? Well, in this case, we need, what does that equation of the line represent? Right? So what we're looking at here is the natural log of SO2Cl2 equals negative K over T plus the natural log of SO2Cl2 initial. So if we're trying to get at K, we want the slope, don't we? So the slope of the line, we see X is the time axis. So we want the slope of the line from that equation. And the slope is minus 2.20. Let's see, slope equals minus 2.20 times 10 to the minus 5. 10 to the minus 5. And that slope is equal to minus K over T, right? So if we just pick a time. Is that right? No. Wait a minute. I'm confusing myself. Minus KT. Oh, minus K times T. What am I thinking of? K times T. There we go. So if we put a value for time in there, this is, I don't know why I'm having trouble with this one. Unless somebody can step in. Yeah. Oh, I am stupid. P is the x-axis. That slope is the K. Well, the negative K. So K is equal to 2.20 times 10 to the minus 5. Some of you must have known that and just didn't speak up. No, no. Okay. Well, what about the peanut gallery? Nobody there said anything. That's what comes working too many of these things. Your brain gets fuzzy. Okay, so 42 m equals 1, that's B. And B also for 43, which should be 2.2 times 10 minus 5. You just get rid of the negative sign because K, the slope is negative, but K is a positive value. I hope that's the last one. Yeah. Okay. Any questions? No? Yep. Yeah, both are B. This all comes under the heading of interpreting graphs.